Okay, welcome to video 3 for the conservation of momentum unit notes. This will be the final video for this unit. To begin with, let's imagine we have two asteroids that are going to collide in space, and they're far from any star, planetary, they're far from a gravitational field, so there's really nothing to interfere with this collision except for the interaction. So here is our first asteroid. I'll call it M1, and it's moving with an initial velocity v1. Then I have a second one, M2. It's moving with an initial velocity v2. When they collide, we will see that there are some forces. And after the collision, let's say they bounce off each other, travel away at velocities v1 and v2. So we want to analyze what's going on here. Well, first off, we can take a look at acceleration. Now, acceleration is defined as the change in velocity for some sort of time interval. So for object 1, we see that it's going to have a change in velocity, and that will equal an acceleration multiplied by a certain amount of time. And these are vectors. Well, we also have something that says that the sum of forces equals mass times acceleration. So for object 1, there's only one force acting on it during the collision. So I could say that the change in object 1's velocity would equal this force 1 comma 2 divided by mass equals t. Now I do need to put a negative sign, and there's a reason. Looking at my diagram, I'm going to say that everything to the right is positive and everything to the left is negative, just like the regular Cartesian coordinate system. So we see that this f1 comma 2 is pointing to the left, so it's a negative force. Okay, I'm going to rearrange some things here. And I'm going to recognize that I have m times v. m1 times this delta v1 right here. Well, m times v is momentum. So what I can say then is that the change in object 1's momentum equals negative f1 comma 2 times t. So if I wanted to make this positive, I guess what I could do is substitute in this 2 comma 1 if I wanted to, but I'm not going to worry about that. Notice also I can do the same exact thing for object 2. And I need to remember that force is a vector as well. So I need to put my vector signs above my force vectors. There we go. So there we have it. We see that change in momentum for an object equals some force multiplied by time. And This second part, this F times time, F delta t, we call this impulse. So what we have here is delta P equals force delta T, or the impulse momentum theorem. Oftentimes we use the letter J for impulse. So we'll say that J equals F delta T. So this is like our formula just for impulse, by itself. We can do a little bit of calculus if we wanted to. Going from algebra to calculus, the triangles become deltas. So the derivative delta P equals F delta T. Or we can say that force is delta P over delta T. Now, we can take a look at what graphs would look like. So if I wanted to plot momentum versus time, and let's say I had some data that looked like this. Well, I would want to take a look at what the slope and the area would represent. So here's slope. Okay, I would have P divided by T. Okay, well, P divided by T, that's force. Area under this line. Okay, that would be P times T. So that would be kilogram meter per second times seconds. That would be a kilogram meter. I'm not sure what a kilogram meter represents. So for the time being, I'm going to say, well, that probably means nothing. All right, well, let's say I wanted to plot force versus time. And let's say I got something that looks like that. All right, slope. The slope would be force divided by time. Well, that would be a Newton per second. Newton is a kilogram meter per second squared. So that would be a kilogram meter per second cubed. I'm not sure if that means anything. Area. That would be a force times a time. Well, a force multiplied by a time, that gives me change in momentum. Or impulse. So the area could be change in momentum or the impulse. Now, notice that a small force acting on an object over a long time can have a greater change in momentum than a large force acting over a shorter contact time. And this explains why follow-through is so important in sports. This is why your coaches are always telling you to follow through. If you can keep the bat in contact with the ball for a greater amount of time, you can give the ball a larger change in momentum, which means that it'll travel farther. If you keep your foot in contact with the soccer ball for a longer period of time, you can give the soccer ball a greater change in momentum, giving it a larger velocity. And when we study projectile motions, we'll learn that that means that they'll fly farther. Okay, now we haven't talked a whole lot about Newton's second law, so let's just, instead of saying a restatement, let's just write it. Newton's second law says that the net force acting on something equals the change in momentum over time. That is Newton's second law. But if we do just a little bit of algebra with it, we can see then that we have this delta V over delta T. And hopefully you recognize that as acceleration. So another way of talking about Newton's second law is F equals ma. So those are the two most common ways of writing out Newton's second law. All right, well, that finishes video 3 and this unit's worth of notes.